Yeah.
Hello everyone, today I'll be talking about generative 3D modeling for deformable objects. I'm a part of the Department of Computer Science at University of Oxford. So I think the crucial part about generative models is the noise that we use, and we essentially aim to predict the noise that exists on an image in order to generate more images. So here, multiple types of noise exist, especially in signal processing. However, we are interested in Gaussian noise because of its additivity, analytical tractability, independence, and memorylessness. So there is something called schedule in while applying Gaussian noise, and this schedule basically maps, a constant where you can basically apply this constant and recreate the existing, the existing image which you have added noise on. So it's like, hey, let's add 5 schedules of noise on this image, and we will basically obtain the same image with the noise. So you can see there are like 2 processes inside diffusion, and like we basically add noise and try to predict noise, and there are 2 processes, forward diffusion and reverse diffusion. We essentially start with data and add Gaussian noise in a series of steps to create a noisy data set, and then basically machine learning model learns to reverse the noise addition to recreate original data from the noisy data set. So basically by showing it a bunch of dog images and adding noise on them, the model essentially learns on its own how to create similar dog images. So there are various applications of diffusion models. Most of you know it by stable diffusion or DALI, where you just type in a prompt and it gives you some 2D image. And nowadays they are using it to augment medical imaging data sets. And another popular field currently is molecule generation for drug discovery and de novo protein design. In the context of graph generative models, you basically add a bunch of nodes and edges randomly, and basically the model learns how to generate novel molecules. So images and graphs, they're all really similar to one another. So what is a 3D generative model? Okay, so a 3D generative model is a diffusion model that runs on top of a neural radiance field. And what is a neural radiance field? A neural radiance field is a function that describes a 3-dimensional object like this coffee cup. You basically describe any object, any 3-dimensional object, with all of its surfaces as a function. And as you optimize this function, you can basically deform this coffee mug into this bottle. And you can basically take this blob, and it's like sculpting, essentially digital 3-dimensional sculpting. So this function takes in 5 coordinates comprising spatial location, viewing direction, color, and density, and it basically maps this object in 3-dimensional space. So there are different types of 3D generative models, and one of them is like, there are 2 types, let's say, and one of them is conditioned 3D generation based on a single image, and there are also other unconditioned 3D generation methods. On the left hand side, you can see a unconditioned 3D generation model called Dream Fusion. You basically just type in a prompt and it generates you the squirrel or any 3-dimensional object basically. However, the problem with unconditioned 3D generation is that it can only learn one type of a dog. So let's say it converges on one type of a dog or a squirrel or a class of objects. Let's say a DSLR photo of a chair, and it will always think about the same chair. You will type in a black chair and it will give you the same chair in black. So it does not represent the class as well. That's why we need conditioned 3D generation, where we feed in an image, we type in a prompt, like in this case we have real fusion, we give an image, we type ballerina, and it converts it into this three-dimensional ballerina object that you can just use in any game or animation. So we have, in the context of deformable objects, we would like to, what I would like to do is, I would like to accelerate this 3D generation process from 40 minutes to 5 minutes to basically under a second. But right now I'm basically able to accelerate it by 8 times by initializing these models using some priors. So here we have a publication named Lassie. How it optimizes the 3D shape is by initializing with a skeleton, initializing with a bunch of neural part surfaces. So instead of optimizing a single blob, it optimizes a bunch of blobs that appears on top of this skeleton. And just like human, it's able to say that this part of the zebra is its head, this part is its neck, this part is its body, and so on and so forth. So we basically deform a bunch of blobs on top of this on top of these key points. So these are some of my some of the work that I've done as part of my MSc thesis, where I obtained some rough meshes from Lassie, and I use SDS score distillation sampling loss in order to add a little bit of texture and optimize a little bit more its geometry, and I basically obtain these really nice looking deformable realistic zebras. So in order to make this process a little bit faster, I tried initializing the model using even rougher meshes like these cylinders that anyone can design in any Unity or Unreal Engine, and the end result was somehow similar to the results that I obtained that I've shown previously. However, the output was like more rough, meaning that there's more work that has to be done in order to improve this rough mesh optimizations. So animation generation using these 3D deformable objects is an entirely different story, because we need a data set, and the model, the machine learning model basically has to learn from a data set where it understands the key points, where the bones are, where the joints are. And this is Magic Pony, a publication that is written by one of my MSc co-supervisors. They basically learn from single view images where the bones of a horse are, and they basically optimize optimize the geometry based on the test image, a given test image. So they first describe the category of horses, and then they optimize the category of horses based on inputs that are given by the user. Additionally, there is this aspect, there is this new publication by them again, but this time they do not use a fixed data set. They imagine the data set using stable diffusion. So the data set, the data set boundary no longer exists. Because they use stable diffusion in order to create a data set of cows, a data set of horses, they are able to represent classes of objects and animals, or basically any object, a lot better than any fixed data set can provide. So given this input image, they first reconstruct it, texture it, animate it, and basically relight it however they like. And their initialization is quite different than Lassie, which I've previously presented. It was made up of a bunch of cylinders. They initialize from this ellipsoid with a bunch of key points inside them. So because their model is trained on this infinite data set created by stable diffusion, they can ask it crazy questions like a cow made out of fruits, and they can basically generate a three-dimensional cow that's actually made out of fruits, because they had like a much larger data set, training data set to describe cows. So dataset quality becomes a real measure when it comes to machine learning and generative models. So thanks a lot for listening to me. If you would like to follow my work, you can add me on LinkedIn or follow me on YouTube. I record videos about the maths behind these models on my YouTube channel, and I hope you enjoy it. And if you are curious, you can ask me.
What would you say the main application of being able to create these deformable objects is?
So the main aim is to give everyone the ability to create animations and games. Like right now, you have to get education in order to use Unity, Unreal Engine, and basically by creating by these 3D generative models, everyone will become a creator, and everyone will be able to create their own animation game without the knowledge of digital design.
Really cool.